Now the next thing we will see is capacity in case of flat fading channels. So we assume that we have a discrete time channel with ergodic and stationary time vary gain, this h of t. We have an input symbol x of t, we have a noise n of t, and then we have an output y of t. And the instantaneous SNR is given by gamma is equal to p bar, that is the transmit power, h of t, channel gain, and the power spectral density of noise. So the capacity in case of flat fading channels depends on two scenarios. So the first scenario is that the receiver knows the value of h of t, that means it knows the value of CSI as well as the distribution of CSI, and the transmitter only knows the distribution of CSI. And the second case is transmitter and receiver CSI. That means both the transmitter and the receiver knows the value of CSI. So now let us take the first case when we have receiver CSI only. So CSI at receiver means CSI is known to receiver at time t, and both transmitter and receiver knows the distribution of h of t. So there are two important channel capacity definitions. The first one is the shaded capacity, that is also known as the ergodic capacity, and the second one is the capacity with outage. So now let us understand this with an example. Let's say we have a bandwidth of 30 megahertz and the channel can take three possible values. 0.05, this is state 1, this is state 2, and this is state 3. And each state has its corresponding probability of occurrence. And with that, each state has the SNR values and the capacity that can be achieved in each of these states. So we can say that when the channel is in state 1, we can achieve 26.2 kbps. When the channel is in state 2, we can achieve 191.9 kbps. And when the channel is in state 3, we can achieve 251.6 kbps. So that means state 3 is better than state 2 is better than state 1. So now what we can do based on this, we can obtain the probabilistic capacity of this channel based on the different channel states. And this is known as ergodic capacity, because we are taking the expectation over all the states of the channel, and this capacity is a function of gamma, and gamma has its own distribution. So then ergodic capacity can be defined as the b log 2 1 plus gamma, the capacity as a function of gamma, p gamma, distribution of gamma, and the integration over the values. So this is what is defined as ergodic capacity. Now by Jensen inequality, ergodic capacity is ergodic capacity is the expectation of capacity over different states, which is defined by integral 0 to infinity b log 2 1 plus gamma, distribution of gamma into d comma. Then using Jensen inequality, we can take this expectation inside. And since Jensen inequality states that E of f of x is greater than equal to E f expectation of x, and this is true when f of x is convex. But here we have logarithm of 1 plus x, and logarithm, we know that logarithm, the behavior of logarithm is head of this, and this is a concave function. So for concave, we will reverse this inequality. So we now have this less than equal to when fx is concave. So we took the expectation inside, and what we get is E, this expectation over B log 2 1 plus gamma is less than or equal to B log 2 1 plus average SNR, that is gamma bar. And it's through the Jensen inequality, we can say that the Shannon capacity of the fading channel with the receiver CSI is less than the Shannon capacity of the AWGN channel with same average SNR. And this can also be verified from the same example. If we try to compute the ergodic capacity, what we have is the probability multiplied by the capacity. So this capacity is achieved for this probability. Then we have 0.5 times the capacity to 191.9, and we have 0.4 times the 251.6, and we can achieve a capacity, ergodic capacity of 199.2 kbps. And this is better because when the channel is in state 1, the probability of the channel to be in the state 1 and having a capacity of 26.2 kbps is very less. So this state 1 does not dominate, but still it helps, it reduces the overall capacity of the channel. Now if we consider the average SNR of the channel, then we have 0.01, the probability multiplied by the SNR of the 1 plus probability multiplied by SNR of the 2, and so on, and then we can get 175.08 as the SNR. And if we try to put this in this expression, B log 2 1 plus gamma bar, where this value is gamma bar, then we can achieve a capacity of 223.8 kbps, and we can see that 199.2 is less than 223.8, and thus the capacity achieved in the fading channel with the receiver CSI is less than the capacity of an AWGN channel when we have the same average SNR. So in ergodic capacity, for the case of low SNR scenarios, in case of low SNR, meaning log of 1 plus x is approximately equal to x log 2 of E, and then we can write rho E of mod of h square log 2 of E. This is the x, that is the instantaneous SNR. And in this case, the capacity of the ergodic capacity is equal to the AWGN channel when this expectation of the channel gain is equal to 1. That is as if we have a time invariant channel. Then next, in case of high SNR scenario, in high SNR scenario, we can write log of 1 plus x to be equal to approximately equal to log of x. And then we have this summation of two logarithms, log 2 of rho plus expectation of log 2 of mod h square. And on solving this, we get log 2 of rho minus 0.83. That means now the ergodic capacity is equal to say AWGN, the capacity of AWGN, minus 0.83 bits per second per hertz. So what it implies is in high SNR scenarios, there is a fading detrimental. That means 2.5 dB of more power is needed in case of fading to achieve the capacity equal to the AWGN channel. So the next is capacity with outage. Capacity's outage is usually considered for the slow varying channels, and that it allows bits sent over the transmission burst to be decoded at the end of the burst with some probability that these bits will be decoded incorrectly. What it means is, let's go back to this example. So capacity with outage means we know that the transmitter do not have any information about the CSI. So when the transmitter do not have any information about the CSI, the possible thing is the transmitter will set the SNR to the worst case scenario to ensure that our system does not go into the outage. So when the transmitter ensures that our system must not go into the outage, that means the transmissions should be reliable. And in this case, what capacity should be achieved when the transmitter wants to ensure that there should be no outage, and it will set a fixed capacity of 26.2 kbps, which is very less. Now if we tell the transmitter that okay, some outage is desired, you can transmit the information, some outage is, we can take care of some outage. So then the transmitter can now set the capacity to 191.9 kbps with an outage probability of 0.1. That means 90% of times we can achieve a capacity of 191.9 kbps. Whereas in the previous case, we say that the outage probability was 0. That means 100% of time we can achieve this 26.2 kbps. And when we told the transmitter that okay, 0.1 outage probability is enough for us, or we can sacrifice some of the performance, then there is a significant improvement in the capacity from 26.2 kbps to 191.9 kbps. So what we mean by this is, as we are telling the transmitter to increase the outage probability, the capacity is increasing. The capacity is increasing. So this is the main realization of capacity with outage. And when the transmitter sets the minimum SNR gamma min, we can encode a data rate C is equal to B log to 1 plus gamma min. And the probability of outage is given as the probability that the SNR is less than this minimum received SNR gamma minimum. And the average rate that is correctly received is given by C naught 1 minus P out B log to 1 plus gamma min, because the transmissions are received correctly in 1 minus P outage. So outage capacity and probability in slow fading. In case of slow fading, for a given channel realization H and the target rate R, the reliable transmission, we have a reliable transmission only if the capacity is greater than this R. Otherwise, we have an outage, and thus the outage probability R of a wireless channel with the target rate R is given by probability that this capacity is less than R. We say that we are in outage.